So at some time t, let the output be at minus Vsat. This means that minus k times Vsat, as I have written over here, is the non-inverting terminal voltage. Now on the inverting terminal side, we have this capacitor and this resistor. One end is at ground, and then this series RC circuit, because this is literally open because there is infinite impedance over here. This end of this series RC circuit is at Vsat, minus Vsat. So this capacitor starts charging towards minus Vsat, and this is how it goes. The capacitor starts charging towards minus Vsat like this. With an intention to eventually level off at minus Vsat. But what happens is that there is this threshold of k Vsat, or rather minus k Vsat, that is present. So as the capacitor voltage falls downwards towards minus Vsat but achieves a value of minus k Vsat, the inverting terminal voltage falls below the non-inverting terminal voltage. And as soon as that happens, the op amp will switch to plus Vsat, as has happened over here. As soon as the output of the op amp switches to plus Vsat, the capacitor turns around from its current value of minus k Vsat and starts charging towards Vsat like this. With an intention to eventually become equal to plus Vsat. Again, as soon as the output switched to plus Vsat, we have plus k Vsat at the non-inverting terminal, and the capacitor voltage rises towards plus Vsat, but at the moment that it crosses plus k Vsat, the inverting terminal voltage has now again exceeded the non-inverting terminal voltage and caused the output to switch to minus k Vsat. So once again, the inverting terminal with the capacitor starts charging towards minus k Vsat. So this is the capacitor voltage against time, and this is the op amp voltage against time. There are two ways of manipulating the frequency of this circuit. One is to adjust the value of k, which is done of course by using the potentiometer that we have allowed ourselves here. This potentiometer will change the value of k, and it will therefore change the switching levels of this capacitor, of the op amp. The other way of course is to change R and C so that the time taken by the charging circuit of RC to achieve that voltage is altered. So for example, if you choose a larger value of R and C, the frequency of the oscillation will come down. This is the Astable multivibrator. So the things to observe here are that there is no input signal. All you have is a square wave output which levels at plus Vsat and minus Vsat of the op amp, and an interesting capacitor voltage that causes the op amp to behave in this manner. So you do the experiment by connecting up the circuit and observing the capacitor voltage as well as the op amp voltage, output voltage, on the oscilloscope on the two channels.
The next part for this experiment is observing the astable multivibrator circuit output. Since Astable multivibrator circuit doesn't have an input, it generates an output. The specification for the resistor and capacitors are mentioned in the handout. We are using a 10 kilo ohm potentiometer so as to vary the frequency for the output. Again, we are generating it through using the op-amp. We can observe the output of this Astable circuit on the DSO. The square wave is the output of the Astable circuit that we are using for generating the waveform. We can change the frequency of this waveform using the potentiometer, that is the pot, by rotating its knob clockwise or anti-clockwise. By changing its knob, we can observe on the DSO that the frequency of this output waveform generated can be changed.
This is the final circuit, a little more complicated than the others. This is the monostable multivibrator. What this does is, there is an input terminal here where you will apply Vi of t. Vi of t is applied as a pulse, a negative square pulse, negative going square pulse that goes below 0. So you have an input waveform which is 0 continuously and goes down briefly and returns to the 0 level. This then is Vi of t. When Vi of t is this, let's see through the different modules of this rather complicated circuit. The first module consists of just this R dash and C dash functioning as a very short time constant high pass circuit. In other words, a differentiator, a simple differentiator. So when you apply a pulse like this at Vi of t, well, let me sketch all the waveforms over here. At this point, which is waveform number 2, this is Vi of t, which is waveform number 1, and this is waveform number 3. And then you have waveform number 4 and waveform number 5. This is waveform number 4 and this is waveform number 5. Let's see what happens at each of these places. Okay, now what has happened is there was a square pulse and this square pulse passes through a differentiator. So the differentiator will do what it does, that is, it will try to be constant, try to be 0 wherever the input is constant and try to give a spike wherever the input undergoes a transition. So this input undergoes 2 transitions, as you can see, one over here and the other over here. There is a downward going transition, there is an upward going transition. So the result, this is waveform number 1. Now waveform number 2 will be this, constant because the input is constant, in fact 0 because the input is constant, and at this point gives a spike which very quickly tries to return to normal and remains normal until this point where the positive going transition occurs. And since the height of the positive going transition is the same as the earlier negative going transition, this will now give a positive spike of approximately the same magnitude. This then is waveform number 2. The next thing to observe is that there is a diode facing towards the left. This diode simply acts as a clipper and rejects positive parts of the waveform number 2 to leave it only with negative parts. So what you get next is only the negative impulses of the differentiator output with the positive impulses removed. So you would get this. This is waveform number 3. All this has happened at the input side. But let's go back in time a little and see what was the state of affairs before this input pulse was applied. All was peaceful. The output was at plus Vsat. And on the inverting side of this op-amp circuit, the following things were happening. We have plus Vsat over here. We have this at ground voltage. And so a current flowed through this part equal to plus Vsat by R. So what was the capacitor doing? The capacitor did nothing because it was shorted across by a positive forward biased diode. So the forward biased diode keeps the capacitor voltage at nearly 0 and hence also allows all the resistor current to pass through itself. So the current essentially, this current I passed through the resistor, through the diode and into the ground this way. And continually until this pulse was applied, this current was passing through the resistor and the diode into the ground. The capacitor voltage was kept practically at 0 or the cut-in voltage, whichever you would prefer. So that is the state of affairs until this pulse got applied. This pulse, waveform 3, is experienced by the non-inverting terminal. This non-inverting terminal, which was literally at 0 volts because the diode was forward biased and shorting the inverting terminal to the ground, now goes below 0 because of this negative pulse, waveform 3. This negative pulse therefore causes the op-amp output to switch to minus Vsat. And temporarily we observe what would happen to waveform 5. Because this is getting quite crowded, I'll draw a new waveform over here. And at this point, until this point, this was at plus Vsat, and what we are drawing now is waveform 5, which is the output of the op-amp. And here we have the 0 reference, and at this point, the op-amp output went to minus Vsat. As soon as the output went to minus Vsat, on the inverting side, several things happened. This is now minus Vsat, this is ground. So the diode gets reverse biased and acts as an open circuit. That's as good as saying that we can take the diode out of the reckoning and just look at this as a capacitor charging through the resistor, C charging through R. So the capacitor, which was earlier at almost 0 volts, starts charging now towards this voltage of minus Vsat. And as the capacitor charges, a point is reached when its voltage crosses the voltage of the positive side. That time that the capacitor takes to charge over to the other side is determined by the values of R and C. The complete waveform is drawn over here. As we said, the capacitor starts charging towards minus Vsat and crosses this level of minus k Vsat at a certain point of time until the inverting terminal voltage goes below minus k Vsat. The output remains at minus Vsat, and this green waveform is the minus Vsat waveform number 5. I actually should have used a different color for the capacitor signal, so let me use yellow over here, and this is the capacitor charging curve. So the capacitor is charging downwards towards minus Vsat, and at a certain specified point of time will cross k times minus Vsat, which is this point. And as soon as it does that, the op amp returns to its previous static state, which is plus Vsat. So the entire history of events can be summarized as follows. A negative pulse was applied here, giving rise to a negative impulse and a positive impulse at this point, waveform number 2. Waveform number 1 is the negative pulse. Now at number 3, at waveform 3, which is the non-inverting terminal, only the negative impulse is applied, and this negative impulse causes the op amp to transition from its normal state of plus Vsat to temporarily to minus Vsat. Now when it transitions to minus Vsat, here we have minus k Vsat as the new non-inverting terminal voltage. The pulse in the meantime has come and gone, so we have minus k Vsat over here. And with the inversion of this to minus k Vsat, the diode is now reverse biased and open, and is therefore eliminated from the circuit for better understanding. This inverted diode, now this reversed diode is now open, and therefore this minus Vsat is the voltage to which this capacitor will aspire to charge through R. So this RC circuit charges downwards as shown in waveform 4 over here towards minus Vsat. It crosses the non-inverting terminal voltage of minus k Vsat at a certain point of time, and that point of time is where the op amp switches back to plus Vsat, the diode turns on once again, and the capacitor becomes deactivated, and a current steadily again flows of value equal to I, and passes through the resistor and the diode and goes into the ground. Now again the monostable will remain in this state indefinitely until another pulse is applied at the input. What you do when you carry out the experiment is you apply a repeated train of pulses to the monostable, because only this can be seen on an oscilloscope, and at each occurrence of an input pulse you will see that there is an output pulse of a specified fixed width of t seconds, where t is determined by the values of RC and the value of k. So this phenomenon repeats itself over and over again. The interesting part is this: the pulse width of the output depends only on k and on RC. It does not depend on the pulse width of the input signal. The input signal that is drawn as waveform 1 over here does not determine the output signal pulse width, because all that happens after all this processing with the diode and the high pass circuit here is that one negative impulse is extracted from this and passed on to the non-inverting terminal to cause it to shift its state. So the monostable is special because it gives you a pulse of specified width at a chosen instant of time, and that width is not determined by the input signal but only by the parameters of the circuit itself. So when you carry out your experiment, you will get an opportunity to observe all these 5 different waveforms, though only 2 at a time because the oscilloscope has only 2 channels.
Now the last part of this experiment is to observe the monostable multivibrator circuit on the DSO. We are giving an input square wave signal of 1 kHz frequency of 2 volt peak to peak to this monostable multivibrator circuit. The circuit diagram is given in the handout. We can observe the waveforms on the DSO. The input signal is a square wave, which we can see that through that the yellow line shows the input signal and the blue line is the output. That is, it is giving a small pulse output and returning back to its stable state. The pot or the potentiometer that we are using in the circuit can be used to vary the width of the output pulse being generated. The pulse width can be varied by moving this pot knob clockwise or anti-clockwise. As can be seen on the DSO, the width is being varied as we move the knob clockwise or the anti-clockwise. Hence we are able to observe the output of this monostable multivibrator on the DSO, in which we were able to produce a pulse whose width can be varied using the pot. Thank you.